Hello friends, welcome to engineering tutorial. So we'll continue our discussion on projectile motion. Previously we discussed questions on projectile motion with horizontal projection. So in the next series of videos we'll be touching the second part, which is projectile motion with angular projection, and discuss questions on that. So this is the first question. It is given that a ball is thrown at a speed of 28 meter per second in the direction 30 degree above the horizontal line, the horizontal axis. We have to calculate the maximum height reached by the ball, its total time of flight, and the total horizontal distance covered by the ball. Okay, so here, like we did in the previous case also, there are two approaches. First is the formula approach. If you remember the formula, you can directly put the formula, get the result. And by chance, if you're not able to recall the formula, there is the resolving into components using equations of motion. That approach, it can take a, it is bit lengthy, but you will get the result. So depending upon you, you can choose any of the two approaches, but I suggest you that you remember the formula, try to remember the formula, so that it will save you a lot of time. Here we'll be using both the approaches. So first let us use the formula approach. So here it is given that, let's say we have a person or a boy who is standing on the ground. He throws a ball in this direction, okay, where it makes an angle of 30 degree with the horizontal line. Okay, the initial speed velocity, that is 28 meter per second. So first it has been asked to find the maximum height reached by the ball. So the ball, it will have this kind of a trajectory, okay, like this. Finally it will reach here. So this is the maximum height reached by the ball. So the formula for h max, that is the maximum height, that is equal to u square sine square theta by 2g. Okay, u square sine square theta by 2g. So basically, if we put the values here nothing has been mentioned about the acceleration due to gravity, so we'll take 9.8 meter per second square. So we'll simply substitute the values. 28 square in place of u square, sine square theta, sine 30 degree square by 2 into 9.8. Okay, so sine 30 degree 1 by 2. So here the result is coming around 10 meters. This is the maximum height reached by the ball. Okay, then the total time of flight. So again, the formula for total time of flight, that is equal to 2u sine theta by g. Okay, time of flight is equal to 2u sine theta by g. So again, we'll put the values, 2 into 28 into sine 30 degree, that is 1 by 2 by 9.8 meter per second square. So the result is coming around 2.857. So rounding it off, so it's 2.9 seconds. Okay, 2.85 like this it's coming, so rounding it off, 2.9 seconds. This is the time of flight. So time of flight is 2.9 seconds. Okay, and then it has been asked to find the net horizontal distance, that is the horizontal range. So if you recall the formula, we have derived all the formulas in the basic discussion. 3 videos were there. First, projectile motion basic concepts, projectile motion with horizontal projection, and then projectile motion with angular projection. So please watch those videos. There I have derived all the formulas. The component approach, where resolving all the parameters into the individual x and y components, the analysis using the equation of motion, it has been done there. So please watch those videos first. Then it has been asked to find the horizontal range. So horizontal range formula, that is equal to u square sine 2 theta by g. U square sine 2 theta by g. So 28 square into sine 60 degree by 9.8, so root 3 by 2. So here it will be, it's coming, the result it's coming around 69.3 meters. Okay, 69.3 meters. So the horizontal range is 69.3 meters. So this is the formula based approach. If you remember the formulas, it's alright. Simply put the values, do the calculations, and you will get the result. But suppose you are not able to recall the formula, then what to do? Well, instead of completely missing the question, even if it's lengthy, go for the component analysis approach, which we'll discuss next. So now let us use the lengthy approach in case you forget the formula. So the situation stays the same, that we have a person who has thrown a ball with a speed of 28 meter per second, making an angle of 30 degree with the horizontal. So here we have to resolve everything into the horizontal and vertical components, x and y axis. So first let us draw the trajectory. So it will be something like this. Okay, this is the maximum height, this is the net horizontal distance, the horizontal range, and then we have the time of flight. Now if you remember, we have discussed that whenever an object is thrown with a certain speed, we have two components. First, the horizontal component ux, and then the vertical component, which is called as uy. This angle is theta, so obviously the horizontal component will be equal to u cos theta, and the vertical component will be equal to u sin theta. Okay, this is equal to how much? 28 meter per second. Theta is equal to 30 degree. So ux is equal to 28 cos 30 degree, which is equal to 28 into root 3 by 2, which is equal to 14 root 3. That is equal to how much? 24.248 meter per second. Here I am going slowly and steadily so that you understand. Okay. Then ui, the vertical component of the initial speed, the velocity, that is equal to u sine theta, which is simply 28 sine 30 degrees. Sine 30 degrees 1 by 2, so that is equal to 14 meter per second. Now if you see, if we name this, okay, let's say this point is O, this point, maximum height point, let's say that is P, and this point is Q. So for the journey from O to P, the maximum height point, for this journey, the net vertical displacement Sy, that is equal to h max, the maximum height. Okay, the vertical displacement is this much. Then we have ui is equal to 24.248 meter per second. Now for the journey from O to P, for the vertical motion, which is upwards, okay, again for this journey from O to P, there is a horizontal displacement and then there is a vertical displacement. It has two motions combined, the horizontal motion and vertical motion. So for this upward vertical motion, acceleration due to gravity is acting downwards, it is opposing it. So for O to P, upward motion from O to P, for the vertical upward motion from O to P, acceleration due to gravity, as it is opposing it, it is in the opposite direction of the motion, it will be minus g, minus 9.8 meter per second square. Now we use the equation of motion, this v square minus u square is equal to 2as. Okay, this is the equation of motion. So here we will substitute it for the y components, that is vy square minus uy square is equal to 2ay sy. Here another important thing to remember, the horizontal component of the initial velocity, that is ux, which is equal to u cos theta, it always remains constant throughout the journey of the ball. Why? Because there is no accelerating or decelerating component in the horizontal direction. Ax is equal to 0. But the vertical motion is different. Here we have acceleration due to gravity. So for the upward journey, okay, the upward journey, the acceleration due to gravity opposes the vertical component of the velocity. So at the highest point, even though the horizontal component is the same, it stays the same, that is equal to Vx is equal to Ux is equal to u cos theta, there is no vertical component. The horizontal component, it stays the same, it is constant throughout the journey. The horizontal component is constant. But at the highest point, the vertical component of the velocity is 0. That is, here at point P, Vy is equal to 0 meter per second. It keeps on decreasing. It keeps on decreasing up to this point. And then beyond P, from the journey from P to Q, downward journey, acceleration due to gravity again supports the downward motion. So the vertical velocity component, it keeps on increasing. From O to P, vertical velocity decreases, becoming 0 at P. From P to Q, it increases, becoming maximum just before touching the ground. But the horizontal component of the velocity, it always stays the same. Okay. Now Vy is 0 at point P. So when we substitute the values, we will have 0 square minus uy, which is equal to 14 meter per second. 14, sorry, here it is 14 meter per second, okay, no, not 24.48, okay. This is 14 meter per second. By mistake I have written 24.248. So it is 14 meter per second. It is 14 meter per second, okay. So here 0 square minus 14 square is equal to 2 into minus 9.8, because ay is equal to minus g, into sy, which is equal to h max, the maximum height. So that implies minus 14 square is equal to minus 2 into 9.8 into h max. So both sides minus minus, they get cancelled. So that implies h max is equal to 14 square by 2 into 9.8. Okay, so it is coming 10 meters. The same result as we obtained through formula, because we derived it using the same principle. So in case you forget the formula, you can always use this approach. So this is the basic equation of motion. This is the same equation of motion applied to the y axis, principle of independence of motion, okay. Then the time of flight. The next part is calculation of time of flight. So here, for the entire duration, okay, for the entire journey, the net displacement along the vertical axis or y axis, what is that? Here it starts from O and it reached the same level Q. O and Q, they are on the ground at the same level. So vertical displacement, net vertical displacement for the entire journey from O to Q, that is equal to 0. So for the entire journey, from O to Q, the net displacement along the y-axis, that is equal to 0 meter, yes. Then the initial vertical component of the speed or the velocity uy, that is equal to u sin theta 14 meter per second. Then the acceleration due to gravity, that is equal to minus g minus 9.8 meter per second square. And then we have the total duration. For the total duration, we have to consider the time of flight, because we want to calculate time of flight. And now we have to use this equation of motion. S is equal to ut plus half at square. Here we'll make these substitutions. That is, Sy is equal to Uy Tf plus 1 half Ay Tf square. So Ay will become minus g, so it will be, that implies Sy, which is equal to 0, is equal to Uy, which is equal to 14 into Tf minus 1 half into 9.8 into Tf square. Okay, so that implies 14 Tf is equal to 1 half into 9.8 into TF square. So TF will become, one side will get TF, as time of flight is equal to 14 into 2 by 9.8. So it is coming around 2.857 seconds. So rounding it off again, 2.9 seconds. Okay, same result. Time of flight is equal to 2.9 seconds, because the derivation part is the same for both. The analysis part, we use the same analysis part to get to the formula, the representation, the basic format. So you will get the same result. So time of flight again same, 2.9 seconds, using the component analysis, x and y component analysis. Now we have to calculate the horizontal range. So the total horizontal distance covered by this entire ball during the time of flight from journey from O to Q, that is equal to r. So again we will use the same formula for the x-axis, the x component analysis. That is, here it will become Sx is equal to uxt plus 1 half ax t square. But here we know that there is no accelerating or decelerating component along the x-axis. So ax is equal to 0 meter per second square. So this whole thing will become 0. So for the entire duration, for the entire journey, Sx is equal to the net horizontal range, horizontal distance, and this t will become the time of flight, and ux, which we all know, that is equal to u cos theta. So r will be equal to u cos theta into tf, which is equal to, u cos theta is 24.248 into time of flight, which is equal to 2.9 seconds. So the result is coming 69.3 meters. 69.29, so it's rounding it off, 69.3 meters, which is the same result. R is equal to 69.3 meters. So again, whichever approach you use, whether you use the formula approach or the component analysis approach, you will get the same result, but always have the formula ready with you. You remember the formula so that you can save time, put the values, get the result. If in case you forget the formula, you're not able to recall it, then you have this approach also with you. Just prepare this in this way, so that you have a backup plan in case you forget the formula. Okay, so this is the first question about projectile motion with angular projection. We used both approaches.